Hey guys, so here is lesson 4 out of torque. We're going to look at lesson 4 and 5. We're just going to look at specific examples of types of equilibrium problems. There's nothing new here. It's just how do we go about dealing with these torque concepts in very specific, kind of specialized cases. The first one is going to be beam problems, which is one of your classic torque situations. So shown below are two beams. We're just going to draw some force diagrams for each beam. Some free body diagrams. So here we go. We've got FG acting downwards here. These beams all have mass. So we want to include those as well. So you've got FG downwards here. There's going to be a force of tension up there. And now there's going to be forces acting here. This is where the hinge is located. So this hinge is going to do two things. One is it's going to hold this guy up this way. And two, it's also going to provide a force this way. So there's a normal force kind of pushing the hinge off the wall, and then the hinge is actually going to provide an applied force upwards. There's no really good thing to call it other than that. Because if this force doesn't act upwards here, it might not be obvious to you that is, but let's talk about why. I've got two forces acting downwards. I've got this force acting upwards here. If this force doesn't exist, what's going to happen to the beam? Well, this is just going to, swing down here. So to prevent this beam from just dropping, there has to be an upward force applied here from the hinge. Same kind of thing with this guy here. This is going to have an FG straight down. This is going to have an FG straight down here. Again, remember, gravity always acts down. This guy's going to have a force of tension up this way. This guy is still going to have an FA, an applied force up here, and a normal force out this way. The only difference here now is you've got to deal with, these ones are a little bit harder, obviously, because things are up at some angle. So there is, the force from the hinge is actually going to act up this way in both of these cases. And this normal force and this applied force are just acting kind of as components of each one of these. So this is the kind of the situation that we have here. To solve these kinds of problems, we could look at force components. We could say, okay, well, tension's acting up at an angle, so I've got a perpendicular component acting up this way, and I've got some distance to the pivot. In this case, the pivot is almost always going to be the hinge. Or we can just use the expression that we had before, where we had torques are equal to the force times the distance between, or distance from the pivot times the sine of the angle between them. Instead of breaking things clearly up into components and using those components, I can just use this expression here, torque equals FR sine theta. Away we go. So we're going to do, how many examples do I have here? I've got 2 examples that we're going to do, and then you guys can work on some of these practice problems. There we go. First one. I got this guy here. I want to find the tension and the force exerted on the hinge by the beam. This example is already broken up for us in some steps. The solution says to use a balanced torque equation to find tension, to use the balanced force equation to find the components of the hinge, and then you want to change the components to polar form to find the force exerted by the hinge on the beam. So first thing we're going to do, always, is our free body diagram. This guy has an FG down from the load, and this guy's going to have an FG downwards from the beam. There's going to be a tension acting upwards here. Tension. And now the hinge is this guy here. We're looking for the force on the hinge. there is going to be a y component, sorry, an x component there, and a y component here. I know I called them an applied force upwards and a normal force outwards. In the previous diagram, I mean, again, it doesn't really matter what you call them, as long as you recognize what they're doing. The upwards force, that applied force pushing upwards, and that normal force kind of pushing outwards, are equivalent to this idea of Fx and Fy combining to give us some sort of F hinge off that way. It doesn't really matter what you call them, they're doing the exact same thing. Okay? So when we're finding the force exerted by the hinge, this is how we're going to break it up. This is sufficient to start, but you can see kind of here where we're going. When we start to break this thing up and talk about balanced force up and downwards, using torque equals Fr sine theta will work for torques, but that isn't going to be enough when we talk about balancing out our forces. And so what you want to do when we're dealing with these guys here is you're still going to want to break this guy up into a force tension Y and a force of tension X. And here we go. So that's everything we've got drawn. Let's make our way through this thing. So we've got static equilibrium. Implies a few things. First, my torques are balanced. So my torques clockwise are going to equal my torques counterclockwise. And the question is always, where are we going to place the pivot? Now, the obvious place to put the pivot is at the hinge here. We don't know what that force is, and so we want to eliminate it. We want to eliminate the torque provided by it, so that's where we're going to put the pivot. Which leaves us with these two forces and this force here. This guy's going to create a torque that way, this guy's going to create a torque that way, this guy's going to create a torque that way. And we're going to call this way positive, as we always do. So my torques are going to be clockwise equals torque counterclockwise. Then I've got my two FGs acting clockwise. So I'm going to have, I'll call this FG beam times R beam plus FG load R load equals FT. Now remember two things. Torque equals F perpendicular R. It also equals FR sine theta. Now these two are perpendicular already. Our tension force is not. So for these two, we're going to use this expression. For the tension, I'm just going to go straight to FR sine theta. So it's going to be my tension times, I'll call this RT, sine of 30 degrees. I can fill some stuff in here. FG beam is, we know the mass of the beam is 0.22, so the FG of the beam is going to be 0.22 times 9.8. The distance from the middle to the pivot, the total length is 0.82, so that's going to be 0.41 plus FG load. Now FG load is, do I know what load is? Yes, 0.7 kilograms. It's going to be 0.7 times 9.8 times the full length of the beam, because the load is at the end. So it's going to be 0.82 equals the tension times the distance from the pivot, because the thing's acting at the end, is going to be 0.82. We've got the sine of the angle between them. So that's my expression that I've got here. This is easy to calculate. let you calculate it. But you'll find that the force of tension should be equal to 15.876 newtons. Done. So now we want to go and find or use the balanced force equations to find the components of our hinge force. So we're going to need two pieces here. We're going to have my forces left equal my forces right, and my forces up equal forces down. Now all of that comes from, all three of these come from the fact that this thing's in static equilibrium. So left equals right. I'm going to have F hinge X. That's my right force. That's a rightward facing force. My leftward facing force is this force tension X. So I'm going to have force of tension X equals my force of hinge X. And then up and down, I'm going to have upward is going to be force of tension Y plus F hinge Y equals, I got two downward forces, FG beam plus FG load. Now FTX is, if I look at what I've got here, if this angle is, if that angle is 30 degrees, this angle here has to be 60 degrees because this beam is horizontal, which means that's a 90. If that's 30, then that's got to be 60. So we're going to have FTX is going to be my tension force sine 60. It's going to equal F hinge X. And I know FT is 15.876. So 15.876 sine 60 equals F hinge X. So F hinge X is going to equal, the value I got for that is 13.746 newtons. And then my FTY, well, that's going to be 15.876 cos of 60 plus F hinge Y, what I'm looking for here, is going to equal FG beam, which is 0.7 times 9.8. Nope. Dang it. Oh, that's the load. Oops, sorry. That's that one. And then FG beam, the mass of the beam was 0.22. So it's going to be 0.22 times 9.8. So solving this, again, you should be comfortable with that. I get F hinge Y is going to equal 1.08 newtons. So not a lot, relatively speaking. Which means that our total F hinge is going to look something like this. I've got a force this way and a force this way. This is going to equal, this is F hinge X, this is F hinge Y. So this is going to be my F hinge. This is 15.876. This is 1.08. So this is going to be the square root of 15.876 squared plus 1.08 squared. And that angle there is going to equal, theta, is going to be the tan inverse of opposite over adjacent. So that's 1.08 over 15.876. Which means F hinge is going to equal, where 13.8 newtons, 4.5 degrees. Now, direction's important. We can't talk about north, south, east, and west because this thing is, go back to the picture, this is up and down. So the way that we would say this is that this angle right there is above the horizontal. Is the language that I would use there. So that is, I mean, they scaffolded this question. They gave us kind of the instructions piece by piece. That is how I would go about doing a question like this. Now, the only thing that you could theoretically do different is you could put values for FG here. I just calculated those in my calculation kind of as I went. But this is how you would set up an equation like this. It's using the ideas of static equilibrium, looking at how all the forces are balanced vertically, horizontally, and rotationally, or the torques are balanced rotationally, to figure out what different forces are going to look like. Do one more example, kind of a little bit more of a gross problem, but the ideas here are going to be exactly the same. Flip the page. You got something that looks like this. When the beam is horizontal, the problem becomes a little bit more complex, since we often need to consider one set of components for the torque equation and a different set of components for the force equations. But okay, like, so we think about what that means here. When we do torque, I'll show you. So what this means here is when we deal with torque, I'll say this. I'll say it this way. Torque needs perpendicular components to the beam, but equilibrium needs vertical and horizontal components. If you use components for torque. Okay, so if you actually break up torque into its its perpendicular and parallel components, this is going to be a challenge, which is why I like to use torque equals FR sine theta wherever possible. Because then we're not going to have to draw an ugly mess here. I'll show you with my pens kind of what I mean here. This guy is up at an angle, this guy is acting off at an angle, so if we were going to use components, we'd have to have one component. This would be my perpendicular component of the force providing the torque. But we would also need, I'm going to do this. We would also need vertical and horizontal components. And we have to draw all of those in because we're going to need my forces being balanced kind of all over the place. To draw all these is gross. It's nice to be able to remove this one by using torque equals FR sine theta. And then these are the only components for the tension force that we have to draw. So I'll show you what this looks like as far as how I would set up this problem. We've got our picture. I'm just going to include this up here first. First, torque equals F perpendicular R, and torque equals F R sine theta. Okay, these are two expressions. True for torque, we want to use the ones that make our life easier. In this case, FR sine theta. Now, here we go. Draw our forces for a free body diagram. This one's going to have this FG load, and we're going to have an FG beam straight down. And I've got I'm going to label it on the bottom here a force of tension. We've got some hinge force acting in some direction. So we're going to label these for what they really are. We're going to F hinge X and F hinge Y. Now I'm assuming that this is acting upwards. It might not be. If we get a negative value here, the hinge force is actually acting downwards, and you'll get that in a question that is coming up here, I believe, in your homework. We don't know which way we're acting, so I'm assuming that it's up. It makes sense that it's up because these two are going to be pulling. This thing's going to be pulling up. These two are going to be pulling down. It's likely that this one pulling down and this one kind of pulling it up at an angle would make this end of the beam kick down. So I'm assuming that the hinge is giving it an upwards push here. We don't know, but that's what I'm going to assume. And then we're going to have the actual F hinge is going to be off this way somewhere. I'm going to draw the components for the tension force in right away because we're going to need vertical and horizontal components. So I'm going to draw it like this. So that's F tension Y. And we've got F tension X going that way. And that meets at a 90-degree angle. We're going to figure out, yeah, we'll do some angle manipulation here in a bit to figure out. Actually, do I do it right now? Yeah, I'll do it right now, just to kind of show you how I would do this. So, we know this angle down here is 28 degrees, we're told. We're told that the beam is up at an angle of 28 degrees. We're told this is 55 degrees. But we want vertical and horizontal components for tension. Well, that's kind of gross. So what we're going to do here is using the angle stuff that I had you guys look at way back in Unit 1, what we're going to do is we had a relationship that said this. If I had two parallel lines and a line between them, then these two angles, alternate interior angles, were the same if these two lines were parallel. So what I'm going to do is I'm going to draw a line right here that is also horizontal because so then that line there and this line here, both acting in the x direction, are parallel to each other, which means that angle there and this angle here are the same. So that's 28 degrees. If this entire angle is 55, then if that's 28, then I know that this is going to be 27 degrees. 55 minus 28 is 27, which means this angle here is also going to be 27 degrees. Because I've got another one of these alternate interior angles here. This line is parallel to that guy. So then this line is going to give us alternate interior angles of 27 degrees, which is going to make this a lot easier to deal with. So there's my free body diagram with all my components on it, and I'm actually going to add some values in here as well, just to make my life a little bit easier. FG beam, we're told this is a 12 kilogram beam. So 12 times 9.8, again, so this is kilograms, that's a mass. Mass times gravity is going to be 117.6 newtons. An FG load, that's an 8 kilogram load. So that's going to be 78.4 newtons. I think that's everything. Oh, no, one more thing. To deal with torques properly, we need the angle between the force and the beam. I'll show you what's going on here. I've got a horizontal component here. These guys are both vertical. I'll do them one at a time. So you can see here, these actually make a right angle triangle. Horizontal and vertical meet at 90. So that's a 90 right there. If that's 28, and that's 90, angles in a triangle, maybe I need to make a note of this here because some of us forget, angles in a triangle, add to 180 degrees. So if this angle here is 28, and I'm going to have a 90 right there, this is going to be 180 minus 90 minus 28 is 62 degrees. And this angle right here is also going to be 62 degrees for the same reason. I guess the triangle just gets bigger. Okay. So now I've got all my angles, I've got all my components that I'm going to need here. I didn't draw perpendicular components for tension because we're going to use this expression here. It makes our diagram a lot less messy. So let's do it. Static EQ gives us 3. Situations. My force is left equal force is right. My force is up equal my force is down. And torques clockwise equal torques counterclockwise. It's important, if this is my hinge, I want to put the hinge where the pivot is. Sorry, pivot where the hinge is, because that's going to eliminate the force we don't know from providing a torque. So if we look here, let's do it first. Let's do the forces left to right, up and down first. So my forces left equal my forces right. My leftward forces is just my horizontal component of tension. So I'm going to have FTX equals force of hinge X. That's my only force acting to the right, or the piece of force acting to the right here. So FTX, that's 27 degrees. That's my tension. So that's going to be force of tension cos 27 equals F hinge X. That's as far as I can go right now. Now my force is up equal my force is down. I've got 2 upward pieces, components, and 2 downward components. So I'm going to have up is force tension Y plus force hinge Y, and that's going to equal FG beam plus FG load. Now force of tension Y, I can put an expression in there. That's going to be FT times sine 27 plus FHY. It's going to equal my beam plus my load. Now my beam is 117.6 plus my FG load is going to be 78.4. So I've got things I don't know. I've got my force tension there, and I've got my force, my hinge X and my hinge Y. And now I've got my counterclockwise and clockwise torques. Now I put the hinge here, which eliminates this, so I just have these 2 and that guy. Now if we look at what's going to happen here, that pivot means these 2 forces are going to create torques in a clockwise direction. So both of these are going to go like this. And this tension here is creating a torque in that direction. I'm going to call always clockwise positive. So my clockwise torques are going to be FG beam times the distance from where the force is acting to the hinge. Now we're told that this is 7 meters long, so this acts at the center of mass. Half of 7 is 3.5. So it's going to be FG beam times, I'll just label it this way. R beam times the sine of 62 plus FG load. I'm going to run out of space here. FG load R load sine 62. That's going to equal, my bad, sorry guys, force of tension, R tension, sine of, and then the angle between my tension and my beam is that big angle of 55 there. Sine of 55. So I can put some values in here. That's going to be 117.6 times our beam is 3.5 sine 62 plus 78.4. It's acting right at the end. So that's 7 sine 62 equals F perpendicular. Now, this is 7. Look at here. This is 1. The distance here is 1.1. So this distance here is going to have to be 5.9. 7 minus the 1.1. 5.9 sine 55. So I'm going to use, this is all valid. The only thing I'm missing here is that FT. So I can solve this. If I solve that, that gives me the force of tension is equal to 175.4 newtons. And now I can plug that in to both of these equations to give me components for the hinge. So this guy over here is going to become 175.4 cos 27. That's going to equal F hinge X. And this is going to be 175.4 sine 27 plus F hinge Y equals, if I add, no, let's leave it the way it is, 117.6 plus 78.4. So I can find hinge X and hinge Y. Force of hinge X is going to equal 156.3. F hinge Y is going to equal 116.34 newtons. And I'm just going to make it really clear what I did. I took this value here, and I plugged it in there, and I plugged it in there. And now both of these are positive, so that means the way I drew them to the right and to the up is correct. So I'm going to have something that looks like this. They're almost the same length because they're almost the same value. This is going to be 156.3. This is going to be 116.34. So there's my F hinge. F hinge, square root of 116.34 squared plus 156.3 squared. I'm not going to write that all out because at this point, that's a right angle triangle. This is Pythagoras. You should be comfortable with that. This is 195 newtons. And that angle right there is the tan inverse of opposite over adjacent. That's going to be 37 degrees. So we wanted the tension. There it is. And we want F hinge. That's 195 newtons, 37 degrees above the horizontal. And I want to make it clear, I didn't have to put a direction for my tension force because it's just, it's right there. It's just drawn, it's in the, we know it's this way. It's drawn in the diagram. What we didn't know was which way the hinge was, so we need to absolutely have that in the answer for that one as well. So that is how you set these problems up. I know this is unique. It's a little different. Do your best with it. Yeah, that's what we got. That is the last question that we're going to look at here. I'm not going to do this example. So what I'm going to do is I'm going to assign some questions for you. I do want you to do 1 to 3. There's 3 different situations for you. I want you to do I'm going to give you 6 as well. And I think that's it. If you want some optional challenge, and when I say challenge, I don't actually mean, like, it's not really that hard, but there are some nuances there that you might struggle with. Take a look at 4 and 5. That's optional. So there it is. These are beam problems, a very specialized version of the static equilibrium torque stuff. As always, if you have any questions, please feel free to ask. Good luck.